Betty, and I'm an associate professor at University College London. And in this presentation, I'm going to talk about some of the research which my colleagues and I have been doing on using ThruMapper, a system for building indoor maps of buildings. Okay, so indoor positioning is an evolving technology, and it makes use of various modalities such as radio waves, magnetic fields, acoustic signals, and other sensors such as those on a mobile phone. There isn't yet a gold standard for indoor positioning, but it is driving the development of indoor navigation applications in places such as these. And in this image here, we have a navigation path inside King's Cross train station, just around the corner from where I work. And a very simple point which I want to communicate with this image is, what is a navigation path without a map? It's effectively just a line. So we need to build indoor maps and have digital floor plans. However, if we don't have these, and this is quite common for older buildings, then we have to generate our own. And crowdsourcing, where we aggregate information from lots of people with sensors on them, that's been shown to work quite well. So this image is from a system called Crowd Inside. And what it does, it leverages mobile phone sensor data, and as people walk around the building, it's able to generate maps such as these. However, crowdsourcing requires a high user density, so it needs lots of people to be walking around. So that isn't always ideal when we have to map areas with a low footfall. But more importantly, techniques such as these require that the users have access to every single room in a building. And this isn't always ideal or possible. So this is an example of indoor mapping using a technology called LiDAR. And both LiDAR and camera SLAM can deliver good resolution. However, here we see a limitation in that the system operator has to access every single room in the building in order to map it. And actually, this isn't always feasible or possible. And if you're trying to map lots of areas with many small rooms, it can be quite time-consuming. So this was our motivation to develop a mapping technique which didn't require the operator to access every single room in the building in order to generate that map. So like I said, that isn't always feasible to have that access. So we propose a radar-based solution because of the ability of radar to penetrate walls and thus overcome those room access and line-of-sight issues which I mentioned with the previous technologies. However, as illustrated in this image, microwaves suffer significant attenuation when they traverse through walls. And this brings about a sensitivity constraint in terms of being able to detect secondary walls and tertiary walls and even walls further into a building. And it's something which we've come up against during our project. In terms of distance measurement, radar is able to use time of flight information to range its targets. And it can do this with accuracies of the order of meters to hundreds of meters, depending on the bandwidth of the signal, according to this term here. To determine bearing information, radar uses time difference of arrival measurements on individual elements of an array antenna. And what this implies is that if we want this angular information, then we have to have a multi-channel system. Also, the accuracy of what we can get bearing information depends on the antenna beam width. So considering these factors, as well as some other elements of radar theory, we propose ThruMapper. And ThruMapper is a phased array through the wall imaging radar, and it's kind of illustrated here. ThruMapper is mounted on a moving platform, so it's able to move through an area, for example, a corridor, and identify signal reflections from the line-of-sight wall, the non-line-of-sight wall, and non-parallel walls. ThruMapper transmits wideband OFDM signals, and that gives us, the idea of that is to give us good axial resolution, so being able to position, locate these walls with a high degree of accuracy. For our angular information, we use two uniform circular arrays, which are illustrated in this diagram. So the transmitter array shown here uses beam steering techniques to sweep beams across a wall and probe it from different angles, while the receiver array, which is shown here, is able to use other types of receive techniques to identify the reflection point on every point of the wall. Well, we've also opted for a full duplex system to avoid TX-RX switching issues. However, because of our system is simultaneously transmitting and receiving, we're subject to something called the direct signal interference, or DSI. And that can be shown here, which is basically the transmitter signals going directly into the receiver array. And this has been a major problem for us. And I'll explain about it more in a few slides, but much of our project has been focused on trying to suppress this interference component. So here's an image of ThruMapper, and here is the corresponding block diagram. ThruMapper is built around the Universal Software Radio Peripheral, which is a popular software-defined radio architecture. We use 4 transmitting and 4 receiving USRPs, and each radio has 2 channels. So in total, we have 16 channels which operate in the Wi-Fi band between 2.4 and 2.48 gigahertz. So we have a wavelength of around 12 centimeters. For the angle information, we use 2 8-element focus arrays, which can be seen in the picture here. And the separation of the 2 arrays is 70 centimeters. And then for all our 16 channels, we have a 120 megahertz bandwidth, again to give us that good position and accuracy on the wall. So once we had conceptualized and built the basic system architecture, the next stage was to develop our enabling strategies and some signal processing techniques, which I'll explain in the upcoming slides. First of all, to identify and then locate both primary line-of-sight walls and the obscured secondary walls, we use a technique called JADE. And JADE is a subspace technique for estimating joint angle and time delays. JADE is an extension of the well-known music algorithm, and it allows us to identify both the line-of-sight and non-line-of-sight walls in terms of range or time delay, tau, and bearing, theta. Our implementation starts off with first smoothing the measured target reflection signals, and that reduces the size of various matrices to help our processing. And then in the subsequent subspace search, the range and bearing of the wall reflections kind of come out to us by as peaks in the space-time JADE surface, which is illustrated here. So what we see in this JADE surface is a peak which corresponds to a wall reflection. The axes are angle of arrival and distance. So ThruMapper tells us at what angle that's coming in at and what range or position that wall reflection is coming in. The direct signal interference, which I mentioned previously in the previous slide, or DSI, that's been a major problem for us. Because basically what it is it's orders of magnitude larger than the reflections from the walls, and that effectively masks that signal. The DSI also imposes a large dynamic range requirement, so it puts a lot of strain on our receivers, and it can saturate the receiver electronics. So to deal with this, and it's highlighted here, so again you see this massive signal going into our receiver. So to deal with this, we've taken a kind of 2-pronged approach, a joint interference mitigation strategy. On the receiver side, given that we know the exact position of our transmitter relative to the receiver, what our approach has been is to selectively cancel the signals coming in from that exact range and bearing using a linear projection technique, which is kind of summarized here. And this technique also allows us to suppress the responses from different types of clutter scatterers in the environment of interest. On the transmitter side, we employ angular antenna lulling. And the way this works is kind of illustrated in this animation. What we do is we steer and fix an antenna null towards the direction of the receiver, while we maximize the gain of our antenna towards the scene of interest and scan that beam throughout. And that, again, allows us to steer null at the receiver and then minimize that interference component coming in and going in. So this is a field experiment to show the effect of transmit nulling. And what we do here is we put ThruMapper in front of a wall and allow it to radiate its OFDM signal. A point to note here is that our our coordinate system is, or the origin or 0 degrees of our coordinate system is slightly off-center or off the horizontal, which is slightly confusing, but due to the orientation of our arrays. But anyway, what we expect is the direct signal interference to come in at around 202 degrees, which is the bearing of the transmitter. And we expect our strongest wall reflection to come in at theta 1 is equal to 264 degrees, which is the point on the wall equidistant between the two arrays. And what we see is that before we apply transmit nullin, in our jade surface, we get a peak at around 200 degrees, which matches that of the direct signal interference. So it's masking, this interference component is masking everything. However, when we apply our transmit nullin, we see that we're able to suppress that interference below the wall reflection, and we get the peak at around 260 degrees, which is what we expect for that wall. Note here that the difference in the two peaks corresponds in terms of time of flight to what we expect. So that's the difference in the propagation path between the reflection path and the direct path. So basically what this highlights is that we're able, in combination, we're able to apply transmit nullin and our receive cancellation strategy to bring that interference below to a level which ThruMapper can then operate. So in a secondary set of experiments, the objective was to put ThruMapper in close proximity to a wall and standoff position to a wall, and just kind of gauge its performance. In the close proximity scenario, we were at 70 centimeters away, while in the standoff position, we were 220 centimeters away. And note, in this presentation, all the walls I talk about are indoor plasterboard walls, and they're of thickness 15 centimeters. So what we have here is the result for both scenarios. The ground truth data is a red dashed line, and the solid white line is the measured data. And what we can see, so what it tells us is where they intersect. So on the measured data, that's the expected angle of arrival and distance. So the red dashed line is is the ground truth, what we expect, and the solid white line is the measured data. And we can see good agreement in both scenarios between what we measure and what the ground truth is. And this kind of highlights that the high angular and range resolution of ThruMapper. The next experiment was geared towards detecting secondary walls. So in this experiment, we put ThruMapper 60 centimeters in front of a primary wall, and you can actually see the response there in the jade surface, and then 225 centimeters away from a secondary wall, remembering that the thickness is 15 centimeters. And what we can see here in the result is we can actually detect, ThruMapper is able to detect the secondary wall. Again, the measured and ground truth data are closely aligned, especially in range, but with degraded signal to noise, signal to clutter, and signal to interference ratio. You can see these unwanted peaks start to come up in the result. So it just shows that we're kind of at the limits at the moment. One of our aims in the longer term is to generate indoor floor plans, in maps of indoor areas. So to do this, we need to combine both our range and bearing measurements into a single point in X and Y. Our delay information leads to something called an ISO range contour, which is equidistant, is a line of equidistance, and it has the transmitter array and receiver array as the focal points. So once we have our ISO range contour, we can integrate our bearing information, and we can then identify the point on the wall which is the strongest scatterer. So in our final set of experiments, we perform a wall scan, because we basically want to start getting into maps of indoor areas. So what we do here is we have ThruMapper at the beginning of the wall, and it scans the first 4 meters in increments of 20 centimeters. And again, it's the same scenario as before. So 60 centimeters away from the primary wall and 225 centimeters away from the secondary wall. And what we do, we put our estimations of both the primary wall and the secondary obscured wall onto a 2D grid, which is shown here. So what we have here is the measurement points of, in over 4 meters in spaces of 20 centimeters. The red squares are the estimated positions of the line of sight wall and the corresponding ground truth in the solid line, and the blue squares are the estimated positions of the secondary wall. Again, the ground truth is the solid line. And what we see here is that ThruMapper does quite a good job of predicting the location of the first wall. However, for the secondary wall, it works quite well in the first 0 to 3 meters, but past that, we start to get erroneous results. And we actually attribute these erroneous results to the corner. And what it is, when we did some further investigations to this, we realized that corners, they present a dihedral structure to the radar. And these dihedral structures are known to have large radar cross-sections. So what we hypothesize is going on is that these strong reflections are dominating and leading to these kind of wrong results. So to investigate this a bit further, we then scan the rest of the wall, but just try to predict the rest of the line of sight wall to see, as we close in the corner, what happens. And we see that the results are correct, for the first few measurements. But then as we close in on that wall, it seems that corner reflections start to dominate, and we get these shallower backscatter returns. So two strategies which we're planning to try and deal with this are, one, we could try and first identify all the corners reflectors in a room, and then selectively use multiple nulling techniques to selectively cancel them out. Or secondly, we can actually use them in our SLAM-inspired RF mapping algorithms. So just to summarize, we have developed ThruMapper, a single mapping robot built around a 16-channel high full duplex high bandwidth phased array radar. It uses null slurring, interference cancellation, and joint time estimation. And we've demonstrated the potential to produce through-wall tomographic maps. But we've still got a lot of work to do, especially dealing with corners. In terms of the future, we want to increase sensitivity to start getting to tertiary walls and beyond. And we also want to move our processing code to the onboard FPGAs to move towards real-time processing. So that's it for ThruMapper, and I welcome any questions. Thank you very much.